is the key to a successfully operating electronic stability platform. If you lose serial data with the yaw rate sensor, it might prompt multiple codes to set in multiple modules. So, let's look at the best way to address these U-type codes. A fault within the yaw rate sensor or circuit will prevent the operation of the ESP. This system utilises CAN for real-time data transfer between the various modules. A yaw rate sensor is used to measure the angular velocity of the vertical axis of the vehicle, then relay this data back to the ESP module. A yaw rate or multi-axis accelerator sensor U-type code will set when there is either an ignition supply or ground circuit fault, or communication via the network can't be established with the device. Make sure the battery is charged and passes a load test before any other task is performed. A weak battery may not supply enough current to operate the modules effectively. Again, when performing this type of diagnosis, it's best practice to attach a battery maintainer to the vehicle. Next, connect the scan tool to the vehicle's DLC and perform a module presence check. Because vehicles use different bus topologies, this should always be done to help isolate and localise the fault. Ensure the sensor harness connector is seated properly and there are no signs of damage or contaminants. With the visual and module presence checks completed, we can now test for communication, reference voltage and ground supply to the control module. As we're inside the cabin, let's use the DLC and a breakout box for a source of voltage and ground. Disconnect the sensor, then turn the ignition on and attach the black meter lead to terminal 5 of the DLC and the red lead to the ignition supply terminal in the harness sensor connector. Ignition voltage should be seen. Depending on the OEM, there may be multiple voltage supply and ground circuits within the harness connector. These will all need to be checked. Next, move the red lead to terminal 16 of the DLC and the black lead to the ground terminal in the harness connector. Ignition voltage should also be displayed. If during these checks voltage supply and ground wasn't present, further diagnosis of these circuits will be required. Please watch our other videos on shorts and open circuits. Referring to our schematic, we can see this bus network uses a linear topology, and we can test the ESP CAN network by connecting between terminals 12 and 13 of the DLC. Turn the ignition off and allow the bus to shut down. Set the meter to ohms and connect between the two terminals. 60 ohms should be seen in a correctly functioning network. If 120 ohms was recorded, this would indicate an open within the network. The meter is only measuring one terminating resistor in the circuit. If a substantially lower reading was displayed, this may indicate the bus network has shorted together. But this will be associated with other related DTCs. Some OEMs may require us to back probe at the module to measure the total network resistance, as they may not be connected to the DLC. Turn the ignition back on and connect the black meter lead to terminal 5 of the DLC, and the red lead to the CAN high terminal in the yaw rate harness connector. Between 2.5 and 3.5 volts should be displayed. Now, move the red lead to the CAN low terminal within the harness connector. Between 1.5 and 2.5 volts should be displayed. If we've proved ignition supply, ground and communication circuits to the sensor are okay, the fault must be within the yaw rate sensor. If the meter displayed 0 volts when testing the serial data circuit, there may be an open or excess resistance. Again, be aware that a short to ground within either circuit will cause other communication codes and may even cause the network to go offline. Any codes relating to short to voltage or ground within the communication circuit should be diagnosed first. Please watch our other in-depth training modules on these procedures. With the ignition on, move the red lead to the next connector in line and back probe the serial data terminal. If the correct voltage is now seen, this confirms the excess resistance or open to be within this section of harness or the connector. Turn the ignition off and disconnect the harness connector. Inspect for terminal tension or corrosion. If this is okay, the fault will be in the first section of harness. If voltage wasn't seen when back probing at the inline harness connector, move the red lead and back probe the next connector in line. In this case, it will be the steering angle sensor. If the correct voltage was seen, this confirms an open or excess resistance between the sensor and the inline harness connector. Although, if the meter still displayed low to 0 volts, turn the ignition off and disconnect the SAS harness connector. Inspect for terminal tension and corrosion. Provided our initial circuit testing is correct, this is the only place the fault could be. Again, the same method of testing could be applied here if using an oscilloscope. An open would look like this, while excess resistance may look like this. Use the scope sample lead as if it were the multimeter test lead. Having the skills to successfully diagnose a communication fault within a yaw rate sensor circuit will reduce the downtime normally associated with these faults. Make sure you don't miss the bus and stay ahead of the game. Thanks for watching. See you soon.